Hello to all of you. Today we are going to speak about thyroid disorders. The thyroid gland is an important endocrine gland in our body and it drives the body. It gives the body the rate at which it should run, or the basal metabolic rate. So today we'll have a short introduction about how the thyroid gland functions, and then we'll go on to the disorders affecting the thyroid gland. First, I would like to tell you some details about the thyroid gland. The thyroid gland, as you would have all learnt, is head-shaped. So it consists of two lobes which are connected by the isthmus. The isthmus will overlie the trachea. It lies in front of the trachea. That is why any thyroid enlargement, people often think hoarseness of voice, I will go take a thyroid test and see. So the dimensions of the thyroid gland, it is 2 cm in length, 1 to 2 cm in width, and 0.5 cm in terms of the breadth or the width. So the weight of the thyroid gland is 15 to 20 grams. Embryology, the thyroid gland is first visible in the developing fetus at day 16 or day 17, and it is first recognized at day 16 or day 17. It is originating from the endoderm. The synthesis of thyroxine hormone in the thyroid gland begins at 11 weeks, and this synthesis is entirely not dependent on TSH. We would have learned that thyroid hormone has higher control from the hypothalamus and from the pituitary. So TSH produced from the pituitary normally controls the production of thyroxine, whereas in a fetus at the 11 weeks of age, it is non-TSH dependent. This is because TSH synthesis itself begins only at 14 weeks of gestational age. In a fetus, the thyroxine hormone is also contributed from the mother. That is why maternal hypothyroidism is given too much of importance. Iodine deficiency in mothers is given too much of importance. So this is about iodine. Iodine, the recommended dietary allowance per day. Thyroxine hormone is synthesized from iodine. We'll see about the synthesis of thyroid hormone in the next slide. So the recommended dietary allowance of iodine is 150 microgram per day in case of adults. In pregnant individuals, it is 200 to 220 microgram, and in children, it is 90 to 120 microgram per day. So this is a slide showing how thyroid hormone is synthesized and how it is transported in the thyroid gland. So we will have 3 compartments: the blood, the follicular cell, and the colloid. So first we look at the histology of the thyroid gland. The thyroid gland consists of multiple follicles. The center of this follicles contains a pink material known as the colloid, and surrounding this colloid we have cuboidal epithelial cells. These cells are known as the follicular cells. There are multiple follicles in the thyroid gland, and in between these follicles we have something known as the parafollicular cells or the C cells. These parafollicular cells are what is going to produce calcitonin, that is concerned with calcium metabolism. Today we will be seeing about the thyroid follicles per se. So colloid is rich in iodine and contains thyroglobulin. Your follicular cells are made up of cuboidal epithelium. We will see how the thyroxine hormone is synthesized. So normally iodine is taken from the diet and is found in blood. It is transported into the follicular cell by the sodium iodine symporter. So since it is a symporter, it transports both sodium and iodine in the same direction. 2 molecules of sodium and 1 of iodide, this is iodide and not iodine, is transported through the sodium iodine symporter into the follicular cell. In the follicular cell, this iodine is again transported into the colloid, where the major process of thyroxine synthesis will be taking place. That is by means of a transporter called pendrin. This pendrin is important in that it is also found in the ear. So there is a syndrome called as the Pendred syndrome, Pendred. So in this Pendred syndrome, people have goiter, thyroid deficiency, and also they have hearing deficit in the form of deafness. Some minimal vestibular balance disturbances will also be seen, but it is not very obvious. This iodine, this step until here, transport of iodine from the blood into the follicular cell into the colloid is called as transport of iodine. It is the first step in the synthesis of thyroxine hormone. Another thing which you will have to know about the sodium iodine symporter is that it is found in multiple sites. It is found in the salivary gland, as it is mentioned here, mammary gland, choroid plexus, and trophoblast also. So if there are disturbances with the sodium iodine symporter, we will be able to see some changes in these organs as well. The most important thing with regard to understanding about the sodium iodine symporter is that this is the one which is involved in the transport of perchlorate, which is therapeutic. That is, in case of thyroid storm, we use this perchlorate, which has to get transported into the follicular cell to exert its effect. That is mainly by the sodium iodine symporter. Also, as a diagnostic procedure, we use pertechnate. to diagnose certain disorders of the thyroid gland. That is also transported through the sodium iodine symporter. Pendred syndrome I have already discussed. So the first step is over, that is transport of iodine from the blood into the colloid. The next step is called as oxidation of iodide. So we have iodide here, this has to get oxidized into iodine. This step is called as oxidation. So that is mediated by an enzyme called thyroid peroxidase. Thyroid peroxidase is also involved in multiple steps in thyroxine synthesis. This is the first step in which it is involved. For this oxidation of iodide into iodine, we require a cofactor called hydrogen peroxide. This is produced by DOX2. DOX2 is necessary for production of hydrogen peroxide. Next, this iodine which is produced by oxidation reaction is coupled with, after oxidation, the next step is iodide. After oxidation, the next step is iodine binds with thyroglobulin in the presence of again the same enzyme thyroid peroxidase to give monoiodotyrosine and diiodotyrosine residues. This is known as organification. The next step after organification is called coupling. We have monoiodotyrosine, meaning one iodine residue coupled with thyroglobulin, and diiodotyrosine, two iodine residues combined with thyroglobulin. These will combine together to form T3 and T4, which are our hormones that are secreted by the thyroid gland. So one monoiodotyrosine with one diiodotyrosine is 1 plus 2. So it is T3 is going to get produced. If two diiodotyrosine molecules are going to couple together, we will get T4. But this T3 and T4 is coupled with thyroglobulin. This T3 and T4 will next be separated from thyroglobulin inside the follicular cell. But before that, we will have to know about this ratio. So normally, one thyroglobulin molecule is bound to 4 to 5 molecules of T4 residue. And in case of T3, it is the reverse, that is one T3 molecule itself binds to 5 thyroglobulin residues. After this production of T3, T4, it is transported into the follicular cell by a process called as micropinocytosis. It is a form of endocytosis. So the endocytosed vesicle is now inside the follicular cell. It will combine with lysosome. Lysosome is an intracellular organelle. It is capable of digesting multiple proteins and degrading bacteria, destroying bacteria. So this lysosome will break T3 and T4 from thyroglobulin. So we get free T3 and T4 and also thyroglobulin separately. Thyroglobulin is circulated back into the colloid, whereas T3, T4 is released from the cell into the blood.